When AC motor controllers break down, it's your job to find out why and fix them. Locating the cause of a controller problem and then correcting that problem is known as troubleshooting. Troubleshooting AC motor controllers is not always an easy job. It takes a lot of skill and resourcefulness to locate the cause of controller problems and then to repair them. You see, every motor controller is a little different, and so are the problems that can occur with them. But by now you should already have most of the knowledge and skill required to troubleshoot AC motor controllers. You should know how to use electrical test equipment and other electrical tools. And you should know the different types of AC motor controllers, their various components, and how those components operate. And you should understand how to read motor controller schematic diagrams. Schematic diagrams are useful tools for troubleshooting controllers. A controller's schematic diagram shows the controller components and how they are electrically connected. From the schematic, you can familiarize yourself with the components of both the motor and the control circuits and how each circuit operates. But a schematic diagram does not necessarily show the physical location of the controller's components. To locate the parts inside the actual motor controller, you need a wiring diagram. A wiring diagram shows both the electrical connections and the approximate physical location of a controller's components as they appear inside the actual motor controller. This wiring diagram shows both the electrical connection and the physical location of the parts of a motor controller that operates the motor driving an industrial fan. Like a schematic, a wiring diagram can be divided into a motor circuit and a control circuit. In this wiring diagram, the manufacturer has already done that for you. The motor circuit is shown with heavy black lines, and the control circuit is shown in thinner black lines. These contacts are shown in heavy lines because they are physically located in the magnetic contactor. But they are auxiliary contacts and operate as part of the control circuit. You can see here that the auxiliary contacts are electrically connected to thin black lines of the control circuit. The outside line is simply a representation of the controller cabinet. The schematic for this same controller looks quite different, but both diagrams contain the same parts. The schematic diagram of a fan motor controller can also be divided into a motor circuit and a control circuit. The motor circuit contains the 3-line leads from the electrical power supply. They're labeled L1, L2, and L3. Also in the motor circuit are the main contacts of the magnetic contactor, the overload heater elements, and the motor. The motor connectors are labeled T1, T2, and T3. Now, let's look at the wiring diagram of this fan motor controller. The motor circuit of the wiring diagram also shows the 3-line leads L1, L2, and L3. The main contacts of the magnetic contactor are also shown. You'll notice that the main contacts are represented by 2 sets of contacts for each power lead, even though in the controller's schematic only 1 set is shown for each power lead. This is because in the actual controller there are 2 sets of contacts for each power lead. Remember, the schematic does not show a physical representation of the controller. It shows an electrical representation, so it is not necessary for it to show 2 sets of contacts for each power lead. But the wiring diagram does. The motor circuit of the wiring diagram also shows the overload heater elements. In this particular wiring diagram, circles are used to represent points of electrical connection. Dots may also be used. The motor is not shown but its leads are. The motor leads are labeled T1, T2, and T3, the same as in the controller's schematic. Now, let's look at the actual controller and try to locate these components using the wiring diagram as a guide. In the wiring diagram, the 3 power leads were at the top of the controller. So to find the 3 power leads inside the actual controller, you look at the top of the controller. As in the wiring diagram, they are L1, L2, and L3. The 3-line leads are electrically connected to the magnetic contactor. If the covers on each side of the magnetic contactor were removed, you could see the main contacts. They would be positioned as shown in the wiring diagram. These contacts would be towards the front of the contactor, these towards the back of the contactor. From the magnetic contactor, 2 leads are connected to the overload heater elements. The 3rd lead, T2, is directly connected from the contactor to the motor. From the heater elements, T1 and T3 are directly connected to the motor. Inside the actual controller, the connections between the magnetic contactor and the heater elements in the overload devices are made with these conducting bars. From the heater elements, T1 and T3 are directly connected to the motor. As in the wiring diagram, T2 is directly connected from the magnetic contactor to the motor. Now that we've located the parts of the motor circuit by using a wiring diagram, let's look at the control circuit. We'll begin once again by referring to the controller's schematic diagram. On the schematic, you can see that in the control circuit is the magnetic contactor's operating coil. In series with the operating coil are the overload contacts and a momentary contact master switch, and a sealing or maintaining contact. For troubleshooting purposes, the numbers 1, 2, and 3 represent common points of reference between the wiring diagram and the schematic diagram. The control circuit also contains the stop button of the controller. In the wiring diagram, the operating coil is positioned in the center of the magnetic contactor's contacts. As it was on the schematic diagram, the operating coil is represented by a circle with the letter M inside of it. To the left of the operating coil, and electrically connected to it, are the auxiliary contacts. In this situation, the auxiliary contacts are used as the maintaining contact. The push buttons are connected to the controller at these points. Since the push buttons are not physically located in the controller cabinet, the numbers signify where the electrical connections are made to the controller. They also correspond to the connection points in a separate figure of the start and stop push buttons. In series with the operating coil are the overload contacts. The overload contacts are electrically connected to L2. Now let's locate these parts in the actual controller. The operating coil is located in the controller at approximately the same place it's shown on the wiring diagram. As shown in the wiring diagram, the magnetic contactor's contacts are positioned on each side of it. The auxiliary contacts are electrically connected to the operating coil by this wire and to the master switch by these wires. The overload contacts are located in the overload devices and are electrically connected to the operating coil by this wire and to L2 by this wire. Not all wiring diagrams look exactly like the one we've just shown you, but then not all controllers are the same. The wiring diagram is a guide for the particular controller you are working on and can help you locate its parts, but sometimes more information is needed to further understand the specific controller diagrams you're using. One source of information is called a legend. Typically, a legend identifies the symbols or abbreviations of the main components located in the motor controller diagrams. For example, the legend for the controller we have just been examining shows that the letter M represents the main contactor of the controller. The letters OL1 and OL3 represent the overload device for phase 1 and phase 3. This is true for both the schematic and wiring diagrams of the controller. You'll find a legend to be an extremely useful aid in reading a controller's diagrams. Another helpful source of information is called a sequencing or switch development chart. A sequencing or switch development chart shows the position a switch's contacts are in during various stages of operation. Sequencing or switch development charts often accompany limit switches, pressure switches, flow switches, master switches, and other types of switches that have more than one set of contacts. This sequencing chart uses the letter X to show that contact 1 is closed when the valve is fully closed. Contact 2 is closed when the valve is fully open. Notice on the sequencing chart that there is a column for the intermediate position of the valve. The intermediate column indicates what position the contacts are in when the valve is neither fully open nor fully closed. The intermediate column of this sequencing chart shows that both contacts are closed when the valve is in an intermediate position. Now, take the time to review this information in your text. Make sure you can read legends, sequencing charts, and wiring diagrams. When you troubleshoot a motor controller, you'll need to use these charts and diagrams as a guide. As an electrician, you'll often be called upon to troubleshoot motor controllers in your plant. It's an important part of your responsibilities as an electrician to uncover the reason for a controller breakdown and to fix it. Now, there are many ways to approach a situation that requires troubleshooting, but we're going to give you 6 basic steps for troubleshooting an AC motor controller. These 6 basic steps for troubleshooting can help you solve just about any motor controller problem that arises. The 6 steps for troubleshooting a motor controller are to know how the motor controller operates normally, question how the controller is operating during the malfunction, evaluate the problem, inspect the controller, repair the problem, and test the controller to be sure it's running normally. And we're going to explain what to do in each one of these steps. The first step in troubleshooting any motor controller is to know. Now, that is to know how the motor controller normally operates. There are many sources for this information. Operators are one good source. They work with the equipment daily and are familiar with its normal operation. The controller schematic is another good source of information. From the schematic, you can trace the current flow to find out the controller's normal operation. Your plant might have a system description or a technical manual that will provide you with information on the controller's normal operation. But no matter what source of information you choose to use, if you know how the controller is supposed to operate, it'll make it a lot easier to identify the symptoms of a problem. The second step is question. You're going to need to know how the controller is working, what the symptoms of the problem are. The best source of that information is the operator or the person who discovered the controller problem. He can give you some valuable clues to what's causing the malfunction. Now, sometimes you may want to test run the motor to see how the controller is operating. Whether or not you decide to test run the motor depends on the symptoms of the malfunction. Test running a controller can sometimes cause further problems, so be sure to consult your supervisor or follow your plant's procedures before making any test run. After identifying the symptoms, you need to evaluate the problem. That's the third step in troubleshooting a motor controller. Every motor controller has a schematic that shows you the controller's components and how they are electrically connected. The schematic is a valuable tool in the evaluation of a controller problem. Study the schematic carefully. Trace the current paths on the schematic and make sure you understand how the components work normally. Then compare the normal operation with what is happening to the controller during its malfunction. You need to narrow down the possible causes of the problem. You can do this by using the controller's schematic diagram. When you evaluate a controller problem, Always divide the controller into its motor circuit and control circuit. Then eliminate the components that are working correctly in each circuit. By dividing the circuitry and eliminating its working components, you can begin to conquer the controller problem. Once you've narrowed down the possibilities, the fourth step is to inspect the controller. This step includes a visual inspection of the controller and any necessary measurements to locate the cause of the controller's malfunction. But in order to inspect a controller, you're going to need a guide to where its components are physically located. Now, the controller schematic only shows the electrical connections of the controller's components, not necessarily their physical location. To physically locate a controller's parts, you need to use a wiring diagram. When the cause of the problem has been found, it must then be repaired. So the fifth step in troubleshooting a motor controller is to repair it. The sixth and final step in troubleshooting is to test the controller. To test it, operate the controller through each of its operating modes to make sure the controller is operating correctly and that there aren't any other problems. Now, let's take a look at an example of how to use these 6 basic steps of troubleshooting. Remember now, the 6 basic steps of troubleshooting are know, question, evaluate, inspect, repair, and test. The electrician has been assigned to troubleshoot a lube oil sump pump. The first step in troubleshooting is to know how the pump normally operates. In this case, the electrician asks the operator to describe the normal operation of the sump pump. The operator tells the electrician that the push-button station is located near the motor, while the motor controller is in another room. Once the start button is pushed, the sump pump normally operates until the liquid level in the sump lowers enough to operate a float switch. When the preset level of the float switch is reached and the float switch is activated, the sump pump automatically stops operating. The second step in the troubleshooting process is to question. The electrician needs to find out the symptoms of the controller malfunction. From the operator, the electrician discovers that the liquid level of the sump is high. Normally, when the liquid level is high, the motor should start when the start button is pushed. But in this case, it won't. This is the only symptom that the operator has been able to identify. The electrician now undertakes the third step in the troubleshooting process. The third step in the troubleshooting process is to evaluate. To properly evaluate the problem, the electrician must carefully examine the controller's schematic diagram. He mentally divides the controller's schematic into its motor circuit and its control circuit. The motor circuit contains 3 line leads from the electrical power supply, the main contacts of the magnetic contactor, the overload heater elements, labeled OL1 and OL3, and the motor. The control circuit is supplied by a transformer, and the control circuit contains a stop button, a start button, a maintaining contact, the magnetic contactor's operating coil, and overload contacts labeled OL1 and OL3. Normally, when the level in the sump is high, the float switch is closed, making a complete circuit from the electrical power supply to the master switch. When the start button is pushed, current flows through the magnetic contactor's operating coil. The operating coil is energized and closes its main contacts in the motor circuit and the maintaining contact in the control circuit. The motor starts operating. Even after the start button is released, the maintaining contact remains closed, maintaining a complete circuit through the magnetic contactor's operating coil. The motor continues to operate until the liquid level in the sump lowers to a preset value. When the liquid reaches the preset value, the float switch opens, breaking the circuit. The operating coil is de-energized, and its main contacts in the motor circuit and the maintaining contact open, so the motor stops operating. The electrician must attempt to narrow down the possible causes of the controller problem. He does this by eliminating any of the working components of the controller. And since the only symptom the electrician has to go on is that the motor won't start at all, the evaluation step lends him little help in narrowing down the possibilities. A malfunction in any one of the components could prevent the motor from starting. There are no components that can be eliminated as the cause of the problem. So, the electrician must proceed to the fourth step in the troubleshooting process, inspection. Now, since the electrician was unable to narrow down the possible causes of the controller malfunction, he first checks the obvious possibilities. Such components as the power supply breaker, the overloads, loose or broken wires are easy to check and eliminate as possible causes of the problem. First, the electrician checks that the power supply breaker is closed, enabling power to flow through the controller. Then he checks the overload device by pushing the reset button. From experience, the electrician can tell that the overload contacts are closed. The overloads are not the cause of the controller problem. After checking the power supply breaker and the overload device, the electrician must inspect the motor controller for loose or broken wires. Since the controller is energized, the electrician uses leather-covered rubber gloves while inspecting the inside of the motor controller. He carefully examines all the wiring. After a thorough examination, he discovers a broken wire on the operating coil. Upon discovering the broken wire, the electrician immediately pulls the power supply breaker down to open the circuit from the power supply to the controller, so that the broken wire will not cause a short or a ground to occur in the controller. It seems likely that the broken wire has caused the controller malfunction. The electrician must now repair the broken wire. Repair is the fifth step in troubleshooting a controller. He replaces the cover before leaving the area. The power supply breaker must be tagged in the off position. The power supply breaker is tagged in the off position according to plant procedures. Always follow your plant's procedures when working on electrical equipment. After the controller has been tagged in the off position, the electrician must test the controller to make sure it's de-energized. To do this, he uses a voltage tester. The voltage tester must be tested with a known power supply. Then, the electrician uses the voltage tester to test all phases, and all phases to ground to make sure there is no voltage present in the controller. He tests L1 and L2, L1 and L3, and L3 and L2. Each of his readings are 0. Next, the electrician touches one of the voltage tester probes to ground and takes voltage readings from L1 to ground, L2 to ground, and L3 to ground. All of the readings are 0. But before he is certain that the controller is de-energized and can be worked on safely, he once again tests the voltage tester with a known power supply. This test verifies that the voltage tester is operating correctly and that his readings were accurate. He uses a screwdriver to disconnect the broken wire and remove it. Then he will proceed to replace the broken wire with new wire. Once the new wire is connected, the tag can be removed and the breaker closed so that power is available to the motor controller. But the job isn't done yet. The electrician must do the sixth and final step in troubleshooting, test. The electrician must test the controller to make certain it is now operating correctly. He asks the operator to test run the pump. The operator pushes the start button and the motor starts. He monitors the operation and makes sure that the pump stops when it should. It operates normally. The problem has been solved. But not all the problems you'll encounter as an electrician will be as easy to solve as this one. Sometimes you'll find that electrical symptoms are actually caused by a mechanical problem. Many problems will involve complex controllers with several malfunctions. but by applying your knowledge of how motor controllers operate and using the basic steps of troubleshooting, you'll be able to conquer the situation. So take the time now to learn these basic troubleshooting steps so that when a controller malfunctions in your plant, you'll be ready to divide and conquer. In the last segment, you saw how to troubleshoot a motor controller using the 6 basic steps for troubleshooting. The controller problem in the last segment was caused by an open, that is a broken wire, that could be easily detected by a visual inspection of the motor controller. The electrician didn't need to take electrical measurements on the controller to locate the open. An inspection was enough to detect the problem. But often, a visual inspection is not enough to locate the cause of a controller malfunction. Usually, it's necessary to take electrical measurements to pinpoint the cause of an electrical problem in a motor controller. Now, most electrical problems in motor controllers are caused by grounds, opens, or shorts. To locate any one of these problems, it's usually necessary to take electrical measurements on the controller. Electrical measurements can be taken on a controller when the controller is either energized or de-energized. Whenever you work on a motor controller, whether it is energized or de-energized, make sure that you follow all of your plant's safety procedures. Now, in this segment, we're going to show you an example of how to troubleshoot a motor controller that is energized. In the next segment, we'll show you an example of how to troubleshoot a motor controller that is de-energized. As you will see, the testing procedures are different for each situation. This electrician has been assigned to troubleshoot a motor controller that operates the motor driving a fan. The fan motor controller is a semi-automatic LVP controller. From experience, the electrician already knows how this particular controller normally operates. The electrician also knows where the power supply breaker, the push-button station, and the motor are located. Before troubleshooting the controller, it's important for the electrician to find out the symptoms of the problem. So first, he talks to the operator. The operator originally reported the problem, so he's the best person to describe it. The operator tells the electrician that the motor starts when the start button is pushed, but as soon as the start button is released, the motor stops. He also tells the electrician that as long as the start button is held in, the motor operates. After discussing the symptoms with the operator, the electrician test runs the motor to verify the symptoms of the controller problem and determine if any other symptoms are present. During the test run, the electrician can hear the contactor close when the start button is pushed and open when the start button is released. So the main contacts are operating. Once the symptoms of the problem are known, the electrician evaluates the problem by referring to the controller's schematic diagram. The most difficult part of his job is about to begin. From the schematic, the electrician determines the normal operation of the motor controller. Normally, when this controller's start button is pushed, a complete circuit is made from the electrical power supply through the operating coil of the magnetic contactor. The operating coil is energized and closes its main contacts in the motor circuit and the maintaining contact in the control circuit. Current flows from the electrical power source through the motor so that the motor starts operating. When the start button is released, it returns to its open position. But the maintaining contact remains closed, keeping a complete circuit through the magnetic contactor's operating coil. The contactor, therefore, remains closed and the motor continues to operate. Now that the electrician knows how the motor controller operates normally, he has to find out why it's not operating correctly. He does this by dividing and conquering. First, he mentally divides the schematic into its motor circuit and its control circuit. Then he begins to conquer the problem by eliminating the working components in each circuit. In the motor circuit, there are three main contacts of the magnetic contactor, two overload heating elements, and the motor. Because the motor starts and operates as long as the start button is held in, the electrician can eliminate the entire motor circuit. He knows that the main contacts are closing and that the motor is working correctly. If any of these components were malfunctioning, the motor would either not start at all or not continue to operate, even with the start button held in. The electrician can now assume that the problem is somewhere in the control circuit. The control circuit contains a stop button, a start button, with the maintaining contact in parallel with it, the magnetic contactor's operating coil, and the overload contacts. The electrician can immediately eliminate the overload contacts as a cause of the problem because the motor is operating. If the overload contacts were open, the motor would not run, even with the start button depressed. He can eliminate the operating coil because the main contacts in the motor circuit are closing. If the operating coil were malfunctioning, the main contacts would not close and the motor would not run. If the stop button was the problem, current would not reach the magnetic contactor's operating coil and the motor would not start. The only components left that could malfunction are the start button and the maintaining contact. There could also be an open in the wires leading to the maintaining contact. The electrician knows that when the start button is held in, the motor starts and the motor continues to operate as long as the start button is held in. The problem, therefore, is not in the start button. That only leaves the maintaining contact and the wires leading to it. The electrician has now narrowed the problem down to a specific area in the controller. Now he needs to locate that area and its components in the actual controller to inspect them, to try to determine if the maintaining contact or the wiring leading to the maintaining contact is causing the malfunction. The electrician turns a screw to loosen the cover to the controller cabinet. Then he removes the cover. Next, the electrician uses the motor controller's wiring diagram to find the components in the actual controller. The easiest way to locate the maintaining contact and the wires leading to it is to first locate the magnetic contactor's operating coil on the wiring diagram. The operating coil is a good reference point from which to find the magnetic contactor in the actual controller. Once the contactor is found, the electrician can locate the maintaining contact and its wiring. On the wiring diagram, the maintaining contact is on the left side of the operating coil and is shown as rear contacts of the magnetic contactor. Before working on an energized contactor, the electrician follows his plant's safety procedures. He uses leather-covered, rubber safety gloves when working inside the controller. When the electrician has found the wiring connections of the maintaining contact, he inspects them for loose or broken wires or anything else that might prevent a complete circuit through the contact. The electrician finds that the connections are tight, and he cannot find any indication of a problem. So the electrician must take a voltage reading to see if there is a complete circuit to the maintaining contact. If a reading is taken and it shows that voltage is present, then the wires leading to the maintaining contact are all right. The problem is caused by the maintaining contact. The electrician uses a voltage tester and takes a voltage reading at the wiring connection points of the maintaining contact. A voltage is present. He now knows that the wiring is not causing the problem. The malfunction must be caused by a problem with the maintaining contact. The electrician must now examine the maintaining contact. But before examining the maintaining contact, the controller is de-energized by opening the power supply breaker, and the breaker is tagged in the off position according to plant procedures. Then the electrician uses a voltage tester to test the controller to make sure that it is completely de-energized. He uses the same procedures to do this as he did in the previous segment. He is now sure that the controller is de-energized and safe to work on. Now that the controller is de-energized, The cover to the contacts can be removed. The maintaining contact is located on the left side and to the rear of the magnetic contactor. So the electrician removes the left cover so that the contacts are visible. He then manipulates the contacts by hand to check for free movement of the contacts. Doing so, he discovers that the maintaining contact does not close. The electrician removes the movable contacts. He checks for damage or something that could be obstructing the closing of the maintaining contact. He finds that dirt on the movable contacts is preventing the maintaining contact from closing. He removes the dirt from the maintaining contact. Then, using a brush, he carefully dusts the stationary contacts to remove any dirt from them. Then he returns the movable contacts to their original place in the magnetic contactor. He carefully aligns the contacts to ensure that they close properly. Once again, he moves the contacts by hand to check for free movement and to make sure they are closing properly. Next, the electrician replaces the contact cover. Finally, he replaces the motor controller cover. After the cover is replaced, the tag will be removed and the controller will be energized. But his task is not complete until he tests the controller for proper operation. To test the controller, the start button is pushed and the motor starts. When the start button is released, the motor continues to operate. The electrician allows the motor to run a few minutes more just to be sure. The controller problem has been solved. You'll see the same basic troubleshooting steps followed in the next segment when we show you an example of how to troubleshoot a de-energized controller. But for now, take the time to review the material in your text and make sure you understand how to use the 6 basic steps for troubleshooting when working on an energized motor controller. An operator in the plant is having trouble with one of the motor controllers. He calls the electrical supervisor to report the trouble. The problem, a malfunction in a motor controller that operates a turbine room exhaust fan. The supervisor assigns the troubleshooting task to one of his electricians. From experience, the electrician already knows that this particular controller is a semi-automatic LVP controller. He also knows where the control switch, the motor controller, and the motor are located in the plant. The electrician talks to the operator to uncover any symptoms that will aid him in solving the problem. The operator tells him that when he pushed the start button, the green off indicating light went out, as it normally would do, but the red on indicating light never came on. The operator then checked the motor. It wasn't operating. He returned to the push-button station and tried to start the motor again. Both indicating lights remained off. Another check of the motor showed that it still hadn't started. After finding out the symptoms of the problem, the electrician replaces the indicating lights at the push-button station of the malfunctioning controller with indicating lights of an adjacent push-button station. This is to make sure that the indicating lights are not burned out and giving false symptoms. The electrician discovers that the indicating lights are all right and should operate correctly. The electrician then refers to the schematic of the motor controller. On the schematic, he traces the current path to determine how the controller would normally operate and familiarizes himself with the controller's components. Normally, when the start button is pushed, the operating coil is energized and closes its main contacts in the motor circuit and operates its auxiliary contacts in the control circuit. In this controller, both the maintaining contact and the contacts leading to the green indicating light are auxiliary contacts. When the operating coil is energized, the maintaining contact closes. The contact for the green indicating light is normally closed, so it opens when the operating coil is energized. Current flows through the motor and the motor starts. Current also flows through the red indicating light so that it lights to show the motor is running. When the start button is released, the maintaining contact maintains a complete circuit through the operating coil so that the motor continues to operate and the red light stays on. The electrician's first suspicion is that the main contacts of the magnetic contactor aren't closing. But from the schematic, he sees that if that were the case, current would still reach the green indicating light and it would remain on. The main contacts are not closing to complete the circuit to the motor from the electrical power supply. But it appears that the reason is not in the contacts themselves. If the malfunction were caused by the main contacts, it would not affect both the motor and the indicating lights. It would only affect the motor. So, for now, the electrician can eliminate the entire motor circuit as the location of the malfunction. Next, the electrician examines the possibilities in the control circuit. He needs to find a component whose malfunction would cause the motor not to start and at the same time affect both indicating lights. If the start button is malfunctioning, current could not flow through the operating coil and the main contacts in the motor circuit would not close. The motor then wouldn't start. But if the malfunction were in the start button, the green indicating light should still light. There would still be a complete circuit through the green indicating light even if the start button were malfunctioning. So the start button probably is not causing the malfunction. If the maintaining contact were not closing, the motor would run as long as the start button is held in. It would stop operating when the start button were released. But that would not affect the green indicating light either. It would still light. It's possible, though, that the overload contacts opened when the start button was pushed. That would cause the operating coil to de-energize and its main contacts in the motor circuit would open. Its auxiliary contacts would operate and the green indicating light would light. Since in this case the green indicating light is not lighting, the problem probably isn't caused by the overloads. Well, that only leaves the power supply to the controller and the fuses. If a fuse were blown, the power couldn't flow through the controller. The motor would not start, and both indicating lights would be affected. If power were not reaching the controller at all, these same symptoms would occur. It appears likely that a blown fuse or a lack of power is causing the malfunction. The electrician will have to check the fuses, and by checking the fuses, he will also be checking the available power to the controller. The electrician uses a screwdriver to open the controller cabinet. He turns a screw on the right side of the cabinet. But this alone does not open the controller cabinet. This particular controller has a mechanical interlock that prevents the cabinet from opening when the controller is energized. When he turns the screw on the left side of the cabinet, the mechanical interlock is defeated and the controller cabinet can be opened. Next, he uses a wiring diagram to locate the fuses in the controller. Then, using a voltage tester, he takes a reading at each fuse. The electrician checks voltage on the input side of both fuses to check if voltage is reaching the fuses. The reading indicates that voltage is present and that voltage is reaching the fuses. This means that the power supply to the controller isn't the problem. Then he checks output voltage of both fuses. There is no voltage present. This indicates that voltage is not reaching the output side of the fuses. One or both of the fuses must be bad. Now the electrician must determine which fuse is bad. To do this, he must take a voltage reading for each fuse from the input of one fuse to the output of the other fuse. Let's take a look at the controller schematic diagram so that we can see this more clearly. We'll use a circle with a V inside of it to represent the voltage tester. The electrician wants to determine which fuse is preventing voltage from reaching the control circuit. From his previous readings, he knows that voltage is reaching the fuses from the electrical power supply at these points. If he places the probes of his voltage tester at the input of this fuse and the output of this fuse, he will get a voltage reading for this part of the circuit. He will also be reading voltage through this fuse. If voltage is not present, it means that the circuit is incomplete, that an open exists in the fuse and voltage is unable to reach the control circuit through it. If voltage is present, there is a complete circuit and voltage is able to reach the control circuit through the fuse. Once the electrician has determined whether or not the fuse is bad, he will then take a reading for the other fuse. He'll place the probes of the voltage tester at the input of this fuse and the output of the other fuse. This will give him a reading for this part of the circuit and this fuse. Once again, if voltage is not present, the circuit is incomplete, and open exists in this fuse. If voltage is present, then the circuit is complete, the fuse is all right. The electrician takes a reading from the input of one of the fuses to the output of the other. The reading shows that voltage is not present, so the fuse is bad. Then he takes a reading at the other fuse. The reading shows that voltage is present. The fuse is good. The electrician should not replace the bad fuse with a good one until he discovers what caused the fuse to blow. Therefore, his task is not yet completed. A fuse blows when excessive current flows through it. The electrician must now determine what caused the high current flow that opened the fuse. From experience, he knows that a short or a ground in the circuitry could cause a high flow of current. So he once again refers to the schematic to determine where either a short or a ground could occur in the circuitry. Since the green indicating light went out when the start button was pushed and never came back on, it indicates that the fuse probably blew when the start button was pushed. The only components that are directly affected by pushing the start button are the operating coil and the red indicating light. Therefore, in this controller, it is likely that a short occurred in the operating coil or red indicating light. A ground, however, could occur anywhere in the control circuit. The electrician decides to test for grounds first. The control circuit of this controller is open at the start switch. So when the electrician tests for grounds in the controller, he will have to test at the output of each fuse. This will ensure that he tests the complete circuit. The controller is turned off and tagged in the off position. Before the electrician begins his testing for grounds and shorts, he first checks the controller to make sure that it is completely de-energized. When testing a controller to see if it is de-energized, voltage on all phases and all phases to ground are tested. The instrument he uses to test if the controller is de-energized is a voltage tester. After the electrician is sure the controller is de-energized, He tests the controller for grounds. The instrument this electrician uses is a meg-ohm meter. A meg-ohm meter is an instrument that measures high resistance and is used for checking insulation resistance. The electrician could use a multimeter or an ohm meter to test for grounds. Before using the meg-ohm meter, it must be tested. This is done by clipping the two probes together and operating the meg-ohm meter to see if the meter will indicate zero resistance. Then separate the probes and operate the meg-ohm meter to see if the meter will read infinite resistance. Next, connect both probes to ground and operate the meg-ohm meter to see if the meter will register zero resistance. A zero resistance reading indicates that the ground connection is good. After testing the meg-ohm meter, the electrician is ready to measure the resistance to ground on the output of both fuses. He connects one probe to the output of one of the fuses. This will give him a reading from the fuse to one side of the start switch. He takes his reading. The reading shows high resistance or infinity and indicates that a ground does not exist in that part of the circuit. Next, he removes the probe from the fuse and connects it to the output of the second fuse. This will give him a reading from the second fuse to the other side of the start switch. A reading is taken and shows that there is high resistance. A ground does not exist in this part of the circuit. After testing for grounds, the electrician tests for shorts. He'll begin by testing the operating coil. A multimeter is used to test for shorts. It must be set to the resistance scale. The electrician disconnects one lead from the operating coil to prevent a parallel current path. First, he touches the probes together, and the helper zeroes the meter by adjusting the 0 ohms knob. Then a resistance reading is taken. A normal reading for this coil is 40 ohms. Any reading less than 40 ohms indicates that a short exists in the coil. The reading here is about half an ohm, so the electrician knows that a short exists in the operating coil. The electrician removes the operating coil. Before replacing it with a new one, he checks to make sure that the new operating coil is the same size as the old one and he has the same voltage and frequency rating. He then replaces the operating coil with a new coil and begins to reassemble the contactor. Then he replaces the bad fuse with a new fuse of the same type and rating as the old one. The controller should now operate normally, so the controller's tag is removed and the controller is energized.